For our third example, we're going to take a look at a transformed square root function. Now, we can kind of cheat a little bit, I guess. Well, not really cheating. We can use some valid techniques that we've learned in prior lessons. Namely that if we can identify the transformations of this, then we can produce the graph of it. But do we really even need to produce the graph? We know that if you know what the original square root function looks like, you should be able to peg that as 1 to 1 without even having to draw it, just because we should be familiar with the shape of the graph. Now, the transformations here are a horizontal shift and a vertical shift. Those are both rigid transformations. They do not affect the shape, they do not affect the orientation. They literally just pick up the graph and move it to a new spot. So if it was 1 to 1 originally, relocating it to a new location is not going to change the fact that it's 1 to 1. So it is. We're going to take a look at that very quickly, but it's always a question we should ask. Is the function 1 to 1? But that's something that we should be able to answer pretty easily. Now, that being said, again, we don't need to go haywire here with a super precise graph. The idea is to simply get the feel for whether it's 1 to 1 or not. So, as we said, the first operation is this addition of 3 that takes place underneath. That is a horizontal shift. Now, because there's no horizontal reflection or horizontal distortion, we can quite simply take this as the inverse of what we see. We see a positive 3, so the shift is a negative 3 to the left 3 spaces. So instead of having the original endpoint here, we're going to track it over 3 spaces. This then is a vertical shift. It happens after the square root operation. And vertical shifts, vertical transformations are always more friendly. Whatever it says is what you do. So it says plus 2, we go up 2. And this is where our new endpoint is. Otherwise, the shape of the graph should be the same. Now, one advantage of actually drawing the graph is that now we can identify the domain and range, which is actually going to be very important in this problem. Yes, it is 1 to 1, so there's no need to restrict anything, but we really do need to keep track of the domain and range here. The domain of this function, as we can see from where it exists on the x-axis, the domain is from negative 3 to positive infinity. The range, where it exists on the y-axis, is from 2 upward. This is important now. We need to keep track of that. We need to know those things because they are going to affect the inverse function. So, as before, we start with replacing f of x with y. And then we solve for x in terms of y. So working backwards, and again, one of the advantages of going through the transformations is it makes us aware of the order of the operations in the function. So now we know the reverse order. We take the last operation that occurred and undo that first. Y minus 2 is equal to radical x plus 3. The next step is to get rid of that square root. Now, when we inverted the x squared function, we recognized that when we undid a square by using a square root, we ended up with that plus or minus thing, and we needed to carefully choose our way through that. When we're undoing a square root by using a square, however, the exact opposite order, we don't have to worry about that plus or minus thing. In this case, it's a pretty clean cancellation. Well, let's be careful with that. Now, could we expand out the y minus 2 squared? Could we FOIL that out? Well, I suppose we could, but why would we? This is going to be in a great form for using transformations. So we're going to leave it like that. Lastly, we're going to subtract 3. And now we have solved for x, which is the output variable of the inverse function. Now, we're going to rewrite this using function notation. Now, here's where we have to really pay attention to those. See, normally this is a quadratic function. Its domain should be all real numbers. But the same way that when we restricted the domain of x squared to create its inverse, we had to carry that restriction through. Well, we have to do that here as well. We created this as an inverse to a pre-existing function. The characteristics and the restrictions that are built in naturally to that function have to be observed and carried through to its inverse. So, despite the fact that this normally should be quadratic and normally should have a domain of all real numbers, in this case, its domain is 2 to infinity, the range of the original function. Likewise, the range of this function, now this one would make a little bit more sense if we graphed it. The range should be -3 to infinity from the domain of the original. So that's kind of the important thing here, is that we have to remember that between a square, in a quadratic, and a square root function, there has to be a relationship that goes both directions. Namely, that the only way that this guy can exist as an inverse of him is under the restriction that we cut away half of the parabola. So I know we started on this side, but the idea is the only way these two functions can even exist as inverses is under that restriction. In this case, we didn't have to create the restriction, it was built in. But we do have to realize that it carries through. So always be careful with these. Much like when we did function composition, the domain may not be as straightforward as you think. Domain is a characteristic that is not, and range too, it's a characteristic that is not immediately visible. And if you're not thinking about it, you may just look at that and think its domain is all real numbers because it's quadratic, but that is not the case. So we always have to be aware of domain and range. It's one of the reasons why it's one of the first characteristics we learn about for functions. It governs everything that happens with them, whether it's inverses, whether it's just drawing them and understanding what input values you're allowed to get and what output values will be produced. But in inverse functions in particular, you always have to pay attention to the domain and range of the original and any restriction that you impose, and that when we go to the inverse function, that domain and range carries through and interchanges.